Okay, YouTube, in my last video, we explored the relationship between two variable types, say y and x more generally, that were directly varying. That is, we would say that two variable types that vary directly are on opposite sides of the equation, and there's a constant of variation that we call that k. And what I'll point out here is that these x and y are both in the numerator. You could put them both in the denominator, but we typically just list this as y equals kx form. Well, in this video, it's sometimes convenient in math to explore a relationship between variables that exhibit what we call inverse variation. And we say that graphs of things that are, involving such relationships are often hyperbolic in nature and contain several asymptotic values for x and y. But we also would say that anything where we have a statement where, say, y varies inversely with x, it's going to be of this form y equals k over x instead of y equals k times x. So just want to point this out. Another way to list this would be y equals k times 1 over x, where we could say, well, k is really just over 1, and we're multiplying these straight across. But the idea here is that the only thing that sets apart direct variation and inverse variation is that when you notice this here, I notice that, or we could say or y equals k over x, that x and y are on opposite sides of the equation. But notice here that y is in the numerator over here and x is in the denominator over here. And we could manipulate this algebraically all we want, but they will never be on the same quote-unquote level, both in the numerator, both in the denominator. So this type of relationship here, we call this inverse variation, this y equals k over x. And we'll look at a few ways to represent this here. We say examples would include y equals 2 over x, where in this case 2 would be our constant of variation. We say k is 2. In this case over here we would say k would be negative 4. But we can see in either instance y and x on different sides, and they're not on the same quote-unquote level. Same thing here, we would say that our k value is 2 in this case. K is 2. And then out here we would say k is equal to a half. Alright, so a half would be our k value right there. What I want to do is kind of look at how these variables behave when we make a couple of tables for them, because we know that direct variation, in our last video at least, we said was an example of linear growth. As x gets bigger and bigger, y gets bigger and bigger in size. What if we were to say now we're saying y equals 2 over x, where k, the constant of variation, is equal to 2. What I want to do is make a table and then describe the relationship between x and y. So we would say, well, what if I allow x to be, let's say, x is 1 and 2, and how about 4, and how about 8? I'm choosing these conveniently here, but the point I'm trying to make is this. If you were to say plug in y equals 2 over, you say 1, then you would get 2 over 1 is 2. So 2. And if you put 2 over 2, you get 1. And if you put 2 over 4 here, that's going to reduce to a half. Okay? So that'd be 1, that's a half. And if I were to put 2 over 8, that'd be a fourth. Okay? So the idea here is that every time, let's see, x went up by 1, x is going up, went up by 2, goes up by 4. Not so much that it went up by that, as much as what you're going to see here is that what's happening is this is decreasing. Okay, and you can see how that kind of decreases inversely with how much it's increasing. But the point here is, as x gets bigger and bigger, we say as x gets bigger and bigger, y gets smaller and smaller. This is what we call inverse. Direct was x gets bigger and bigger, y gets bigger and bigger. So this right here, this would be direct. And when we talk about inverse, we're saying as one gets bigger and bigger, the other one's getting smaller and smaller more generally. So again, down here, if we had y equals negative 4x, and we went and put in some convenient values like negative 4, how about negative 1, 1, and 4, yeah, those will work for me. So negative 4 over negative 4 is 1. Negative 4 over negative 1, that's 4. And we say negative 4 over 1 is negative 4, and negative 4 over positive 4 is 1. If we were to sketch a graph of either of these relationships here, you would see that, how about at least on this first one, 1, 2, 3, 4, 5, 6, 7, 8, we could see that 1, 2, 3, 4, 5. This is y, this is x. We could see that it was at a height of 1, 2 was one of our solution pairs. 2, 1. You can see that as we keep going to the right and x gets bigger and bigger, you see what's happening. Your y values are getting smaller and smaller. So when we talk about hyperbolic values here, we say that yes, this would be what we call a part of a hyperbola. You notice that y is getting smaller and smaller as x gets bigger and bigger. And when I mentioned there are asymptotic values, we'd say, well, this would never reach a height of 0. And there is an x value we would never plug into an inverse relationship here, but we would never divide by 0. Okay, and so that's why you'll see an asymptote here at x equals 0. So really quickly, there's a couple of alternate forms of inverse variation. I just want to point this out really quickly. This is inverse variation, great, but it's really the same thing as what you've got right here, I think. So the reason why I say this is because when you talk about direct or inverse and identifying them, you want to have variables on opposite sides. So for instance, if I divide both sides by x here, the x's cancel, I get y equals 2 over x. So they are indeed the same thing. So be careful with that when you're identifying. So let's look at a couple of examples here and wrap this up. We say, first things first, when you read these, they're usually word problems. So they'll give you something like variable y varies inversely with variable x, whatever those are. So the first thing we want to do is we want to start by writing a model. And we know that anything that varies inversely, x and y are on different levels, numerator and denominator. So this is our model. The only thing we don't know is k, and k is going to be different depending upon your given situation. So in our given situation, let's keep reading here. It says when x equals 3, y equals 8. So we were given some fascinating information here that when this is true. And what this is going to allow us to do is take this solution pair, plug it back into the original model, and go solve for what the specific value of k must be in this instance. So we say x is 3, y is 8. If we take both sides of this times 3, then we determine essentially that k is equal to 24. So in this particular case, our constant of variation is 24, and our model, and this is really important that we are able to write a model for this given situation. We say in this given situation, we have 24 divided by x. What this is going to allow us to do then is use this equation to predict y. We're going to say, what's y equal to if x is equal to negative 4? And we can actually just go substitute this in. We said, well, then y would be 24 divided by x. When x is negative 4, then we get really this. We get negative 6. So we would say this is here, negative 6. And we could certainly go graph this. And this last example here involves a word problem, but let's read this critically. It says the volume, so that's V. The volume of a gas varies inversely, so there's a key word here, as the pressure P on it. So I'm going to stop right here. I'm going to say, well, volume is inversely proportional to my pressure. So that means that they're on different levels, 1 over P. And there's a variable K out front, or a constant of variation. I think it's a little bit easier to just write volume equals K over P and say, look, they're on different levels. So here's what we're told. We say, well, volume and pressure are related to one another. And it says here, if the volume is 240 cubic centimeters, so they give us a data point, 240 cm cubed, under a pressure of 30 kilograms per centimeter square here. So we get 30 kilograms per centimeter squared. This is what pressure has to be applied to have a volume of 160 cubic centimeters. So we know this unknown is corresponding to this 160 cubic centimeters of volume. We want to know what this would be. And keep in mind that because our volume is getting smaller, then the pressure is actually going up. You're squeezing it down. So we say by what? Well, let's go ahead and plug in our known values here. We say the volume is 240 if and only if this varies inversely and x is equal to 3 or pressure is equal to 30. So if we take both sides of this times 30, we would get, let's figure this out here. We would find that 240 times 30 is equal to 7,200. So what this means is we have our constant of variation is 7,200, and what we need to do is we need to go now find the pressure is what they're asking for when the volume equals 160. So in this case we have now our model is volume equals 7,200, which is our constant of variation, over our pressure. We want to solve for the pressure when the volume is equal to 160 cubic centimeters. So to solve this, I suppose one thing we could do is we could do a cross product since it's proportional. We say 160 P is equal to 7,200. So if we divide both sides of this, or take that 7,200 and divide it by 160, we essentially were able to determine that the pressure would be 45. And we say 45 what? We do want to label this. And pressure was being measured in kilograms per square centimeter, not per square meter. Okay. But that is how you deal with inverse variation. My last video will talk about joint variation.